Okay then, so it's a pleasure to welcome Scott Ransom to give the Origins Colloquium this week. Scott received his PhD in 2001 from Harvard, and then he was a postdoctoral fellow at McGill University in Montreal for a few years, and then I think you then joined NRAO after that. Is that right, Scott?
Yep, that's correct.
Great, and now as a senior tenured scientist at NRAO, as well as a research professor at University of Virginia. And Scott's research focuses on pulsars, many different aspects of pulsars. So a great variety of the science there. But in recent times, has also been heavily involved, well, actually for a long time, in helping to found the NANOGrav collaboration, and most recently chairing it until 2022 at a very exciting time when the gravitational wave background was discovered. And so I think today we'll hear about the latest news on that front. So please go ahead, Scott.
Thanks, Jonathan. Yeah, it's a pleasure to be here and to talk to you about NANOGrav and what's happened, especially in the last year. I know at least here in Charlottesville, there's been a couple NANOGrav talks over the last year. And so if you've heard this, the NANOGrav stuff before over the last year, I'm shortening most of that, and I've tried to expand most of what the implications are to talk about supermassive black holes, potentially new physics and stuff like that that has come out since we made the announcement a year ago. So hopefully there'll be some new stuff, and I've also tried to make it a little bit short so we can have some discussion at the end, and I can hopefully learn more from you guys about the astrophysical implications. Because let me make that clear up front. I'm a pulsar guy, so pulsars are what I do. So the instrument in NANOGrav is based on pulsars, and so the high precision timing and stuff that lets us potentially detect the nanoHertz gravitational waves. That side of things is kind of where my focus is, and not on the supermassive black holes, which we likely think are the source of the nanoHertz gravitational wave background. So that's kind of where I'm going to be going. And please, I do like to keep things informal. So if you have a question or whatever, just raise your hand, or if you're on Zoom, please just speak up. And feel free to ask questions during. So I really like this slide. This is kind of the one very long and convoluted sentence that tells what NANOGrav does, and I find it's mind-blowing. There are so many crazy things that have to come together to make this experiment work. And the amazing thing is I think it's working. So let's go through it really quickly. We use the world's largest radio telescopes to measure pulses from scores of pulsars. The numbers, depending on if you're including just NANOGrav, which is roughly 60 to 70, to the whole international community, it's about 120 pulsars, each spinning hundreds of times per second. We're talking about millisecond pulsars here, which are ultra-stable celestial clocks. And together, those pulsars make the array. That's what makes the detector. It's a galactic scale detector that can detect the Earth, and this is a key point, it's the Earth that's bobbing on the sea of these nanoHertz gravitational waves. And we'll talk about why the Earth is the key component there. And we think it's most likely emitted by all of the supermassive black hole binaries integrated throughout the whole universe. And that's caused by the colliding galaxies that we know happen as cosmic time evolves and galaxies evolve and merge. That's the experiment. It really does, to me, seem like science fiction. This idea was first thought of in basically the early to mid 1970s after pulsars were discovered. A couple different people independently thought of the idea, but it didn't become a reality until millisecond pulsars were discovered in the early 1980s. And then it took decades for us to get big enough telescopes, get the improved observing techniques well enough to be able to precisely measure those pulsars, and to find enough pulsars that the experiment actually became kind of a reality that might actually work someday. Yeah, as Jonathan mentioned, so I am one of the founders of NANOGrav, and our whole goal has been what we announced last year, which was to provide strong evidence for, and notice I did not use the D word like Jonathan did, detection or discovery. We're very, very specific about that. Internationally, the various pulsar timing arrays had agreed on some statistical levels that we would meet, basically kind of the 5 sigma levels that high energy physicists use for a detection in their experiments, in order to say that we detected or discovered the gravitational wave background. So we said we had strong evidence for it, and we announced that last June. And we had a really nice press conference up at the NSF, which is what this picture's from, down on the bottom right there. Those were, notice we have a lot of 5 of our younger members of the collaboration, including Steve Taylor, who's the current chair on the left there, who were up speaking about the results. A lot of great stuff came out that day, a lot of press, and all of our papers were published simultaneously that day, as well as international papers from our international collaborators and competitors. It's a little bit of both, from the other pulsar timing arrays, because we do work closely with them and share a lot of stuff, but we're also kind of competing a little bit. And we all released our results on that same day. It was really exciting. So that's what I'll basically be talking about. The collaboration itself, NANOGrav, has grown hugely over the last 15 years, and it's now basically 200 students and scientists in total. We're very welcoming, very open. If you're interested in what we do, any parts of it, the pulsar side, the gravitational wave detection, the statistical analyses parts, the astrophysical implications about supermassive black holes, or even new physics, we welcome you to join our collaboration. You can just go to nanograv.org, and there's an easy way to sign up. But our mission is to detect the nanoHertz frequency gravitational waves. And nanoHertz is also a pretty key word there. So nanoHertz, 10 to the minus 9 hertz. So we're talking about years duration gravitational waves. So this is really slow gravitational waves that are caused by very special sources that are different than LIGO and what Lisa will see eventually. And because they're such slow waves, you need a lot of time. So this is an experiment that requires a lot of patience. So when we started 15 years ago, we didn't know it would take 15 years, but we did know that this experiment would be ongoing for decades, and as the science would grow with time for the experiment. And that's exactly what we're seeing. So I mentioned our international collaborators and colleagues. So that in general, there are now 4 official pulsar timing arrays. NANOGrav is on the left there. There's the telescopes we use, GBT, Arecibo, the Very Large Array, and CHIME. And it's North American collaboration. We have a lot of Canadian collaborators, including the Canadian telescope CHIME. In Europe, we use the 5 different kind of 100-meter class telescopes that are in Europe. That makes up the European Pulsar Timing Array. The other classical, there were 3 PTAs for a long time. The third one was Parkes, the Parkes Pulsar Timing Array, down here in the bottom right. They use the Parkes telescope. That's currently the smallest collaboration, but the Southern Hemisphere is improving tremendously, because both the Meerkat Pulsar Timing Array, or the South African Pulsar Timing Array, is doing fantastic stuff now. They are not an official 100% officially joined to the IPTA collaboration yet, but their first major gravitational wave results are going to be out. There's draft versions of their papers. They're going to be out within the next month or 2, so you will see them. And that's an incredible telescope, Meerkat. And then the Indian Pulsar Timing Array, which uses the GMRT in India, they're very far south, not in the southern hemisphere, but they can see a huge number of pulsars that are in the south as well. So that's really helped the southern skies. And so they've become an official PTA member recently. And then finally, unofficially yet, they're an observer. They have observer status with the IPTA, is the Chinese Pulsar Timing Array, and they currently have the most sensitive and biggest telescope in the world, which is FAST. And because that telescope is so incredibly sensitive, and because pulsars are so faint, that telescope is going to be hugely important in the future of this field. But right now, the Chinese have been independent effectively. They have not wanted to officially join the IPTA, and so they're not sharing their data with the other PTA members like the other collaborations are. So in general, that's what makes up the IPTA, that shared set of data. Those shared sets of observations from all these PTAs together get us the whole northern and southern skies, get us a lot more pulsars, and get us a lot more cadence and number of observations on those pulsars, so that we can do a better job detecting gravitational waves. So that's kind of the stage. And the whole point is to do this. It's the gravitational wave spectrum. So in analogy to the electromagnetic spectrum, where over the last century and a bit, astronomy has completely opened up that electromagnetic spectrum. We just recently opened up a very slim portion of the gravitational wave spectrum out here on the right with LIGO Virgo. So LIGO and Virgo, you can think of it as the X-rays of the gravitational wave spectrum, because they're at very high frequencies. So the frequencies, and I'll use remember to use my pointer. So the frequencies down here are in the hundreds of hertz up to kilohertz. So it's kind of the very high frequency side of the gravitational wave window. LISA is going to happen next decade and fly for something like a handful of years, hopefully 5 to 10 years. LISA will fly. And it's going to be able to detect things in the millihertz frequency range. We are down here in the nanohertz frequency range on the left side of the screen with pulsar timing array. And that's where, so you can kind of say that we're like the radio astronomy of the gravitational wave spectrum, whereas LISA is kind of like the optical astronomy. So we're different frequency bands, and just like in the electromagnetic spectrum, we have different sources in those different gravitational wave frequency bands. Except primarily, we think the dominant sources are black hole binaries throughout the whole spectrum. So we have the dominant source in LIGO is stellar mass black hole binaries. We have intermediate mass black holes up to say 10 to the 6 or even 10 to the 7 solar mass black holes in LISA. And then in the NANOGrav band, we're talking about 10 to the 8 to 10 to the 10 solar mass black hole binaries. But in general, all of these source classes are very bright. And with these detectors, we can see out hugely, throughout the vast majority of the universe with these sources. About the black holes, notice the colored bands here that are you can see on the screen. Those colored bands represent roughly what we think the black hole stellar mass function or the black hole mass function looks like. So it's a power law. There's and it's in terms of kind of the masses of those black holes. So we're going to see there's a ton of black holes down here in the stellar mass range, many fewer of the most massive black holes on the lowest range, but those provide on the y-axis the most gravitational wave strain. And this whole graph is in units of strain, so I want to talk just a touch about that. Strain in terms of LIGO, because it's an interferometer that uses lasers to measure the distance between test masses. The way that LIGO does things is they measure that change in length, the delta L, over their interferometer arms, and that gives the gravitational wave perturbation scales, which we call strain. We do exactly the same thing in pulsar timing arrays. We're measuring the relative distances and how they change between pulsars and the Earth. And we do that on many different baselines, and we do that, we're measuring those links via measuring when the pulses arrive, because the speed of light is constant. So we're really doing delta t over t, measuring time differences, but because the speed of light is constant, it effectively delta L over L. And I want to point out the numbers that are on the left-hand side here. These are incredibly small deviations. LIGO, it's notorious for, the tiny fraction of the size of a proton that they were measuring the distances for gravitational waves. In pulsar timing arrays, if you look up to the sources where the noise curves of the NANOGrav band is up here, the numbers we're talking about are in the 10 to the minus 14 to 10 to the minus 16 in units of strain. So keep that in your mind, 10 to the minus 15, 10 to the minus 16, because we'll come back to that number. All right, so how does this work? Well, it's because we have these things, which are really incredible for a wide variety of physics. They're neutron stars, they spin, they have this lighthouse type effect. Because there's nothing else around them, they spin very perfectly in a vacuum, and we can time them like clocks. So for our purposes, in an experiment, you can think of them as a clock. And luckily, we have millisecond pulsars, because it turns out that the faster the pulsar spins, they have lower magnetic fields, they spin longer, they spin more stably, and you can measure them more precisely. So the faster they spin, the more precise we can measure them, which is a really, really great thing. And so it's those millisecond pulsars that let us do this type of science. And just to give you an example, We use the technique of pulsar timing, which just go into detail about how it works, except for to say one sentence, and this is really for the students out there, and let me know if you want me to go into this any more detail in the question and answer. But we account for literally every single rotation of the pulsar over decades. That is exactly what pulsar timing means. And even though we're 10,000 times better than that. And when you add that up over years, you get extraordinary measurements. So here's an example of the timing parameters. These are physical parameters from our timing model from one of the other pulsar timing arrays from the Parks group of 3 of our best millisecond pulsars. So each column is a different millisecond pulsar, and each row are different physical parameters that we're measuring. And I just want to point out a handful of them. We use this weird notation also that our numbers are so precise that we put our error bars in that last little bit there in the parentheses. So for instance, the spin frequency of this pulsar has something like 17 or 18 significant figures. That is not a typo. The error bar is 5 in that last digit. And that's changing. That number is changing like as an odometer. About once every 30 seconds, that last digit changes because the pulsar is slowing down with time. And we can easily measure that. So these are some of the most precise measurements in all of physics. On the right-hand side, up here, that's the position of the pulsar in the sky. And we use single dish radio telescopes that have a single pixel. This micro arc second precision in position on the sky, micro arc second here, or at least 10 micro arc seconds, is completely due to measuring the fact that as the Earth goes around the sun and the pulsar's over here, we get an extra time travel delay that we can measure as a sinusoid with a 1-year period. We fit that sinusoid out with exquisite precision and get micro arc second positions. Here's an orbital parameters in the second, the final ellipse there. The orbital period and semi-major axis of this millisecond pulsar orbiting a white dwarf, these are 10 and 12 significant figures. So these orbits are measured, better than the vast majority of the orbits in the solar system are measured, for instance, because of pulsar timing. And we can subtract out all of these effects to get hopefully perfectly flat residuals. So, and I'll show you what residuals are, but we model when the pulses arrive, we measure when they arrive, we subtract the two, and if everything works, our model perfectly explains our measurements. And what we're doing is looking for gravitational waves in what's left over. So our observations, I already mentioned, came from 4 big telescopes. Arecibo was crucial for us. Rest in peace up at the top there. It collapsed, as you all know. I just want to mention Arecibo, until it collapsed, up until the very date, a lot of people thought, oh, it was old and wasn't doing any good science. It was an absolutely state-of-the-art pulsar instrument. There was nothing better in the world at the time. So I just keep that in mind. So it was a big blow to the pulsar community, as well as, for instance, planetary radar community, which there's nothing that really replaced it since then. The Green Bank telescope was our other key pillar. And the nice thing about the GBT in Arecibo had huge sensitivity, but could only see a relatively small portion of the sky. So for the pulsars that it could see, it was always the best. But for the rest of the sky, the GBT could time those very well. So when you combine those two things together, we had about similar gravitational wave sensitivity from each telescope, because the GBT could see much more of the sky. Arecibo could really focus on the pulsars that it could see. Since then, we've now started to lean heavily on the Very Large Array and on CHIME. And the CHIME telescope in Canada has been really interesting for us. Because we've lost Arecibo, we've had to rely more on the GBT and add the VLA. CHIME has allowed us to make low frequency measurements in the hundreds of megahertz, which let us remove the effects of the interstellar medium. And that's a crucial noise source for us. All right, no more about observations. Here's what our data set looks like. And this is a kind of a cool plot that was put together by Thankful Comrade, who's the head of our timing working group. It shows every column here is a set of data for a single pulsar. The colors are the different observing frequencies, and you can see the time starts at the top and moves down to the bottom. And what you can see is that as time has gone on, we've added more and more pulsars. That's been really crucial. The reason why we've added more pulsars is because there's been massive pulsar surveys to look for millisecond pulsars over the last couple decades, and we've been highly successful, and that's allowed us to expand our pulsar timing array. But what you can see is we want to evenly sample as much as possible for all of our pulsars, and we want to add as many good pulsars as we can to make the pulsar timing array better. And the reason for that is that the gravitational wave sensitivity is directly proportional to the number of pulsars. So that's a crucial bit right there. The more pulsars, literally the better, in a linear fashion. We improve, as a lot of experiments do, as the square root of time, but also the precision of every individual measurement is a less important but still important factor, and that's why we need the best pulsars. We can't just throw any pulsar in there because pulsars, slow pulsars for instance, we can't measure nearly precise enough to have them make an impact in the pulsar timing array. All right, so what do these data look like? So this is these are the residuals, the timing residuals, which are once again a prediction of the model, the physical model, when the pulses are going to arrive, minus the measurement of when they actually did arrive. Okay, and this is one of the very best pulsars. This shows clear back from 2004 up to basically the current day or a couple of years ago. And I'm going to focus you on one panel here because there's a lot of information in this, but this is really the key panel. This is where we show the average measurements of this pulsar over time. And as I mentioned, if our model's good, what we should see is a perfectly flat set of residuals. Our model should perfectly replicate what we're measuring. And what you can see is there's a little bit of extra signal in there, a little bit of extra waviness. That could be caused by many things. It could be caused by intrinsic timing noise in this neutron star. If something's going weird in the core or the magnetic field over time. It could be that we're not correctly removing the interstellar medium effects, or it could be gravitational waves, for instance. And what I want to point out is the size of this effect. Notice the timing residuals, the y-axis, are in microseconds, and we're talking about nearly, well, basically 15 years. So let's go back to that strain number. If I can measure deviations of order a microsecond, or in this case, 100 nanoseconds is the precision, over 15 years, the delta t over t works out to 10 to the minus 16. This is exactly how we're able to measure those relative distances between the pulsars that let us make the gravitational wave measurements. All right. The other crucial thing, which you saw hopefully last year when all the publicity and stuff was coming out about gravitational waves, was this curve. This is known as the Hellings and Downs curve. And this is kind of the smoking gun signal that we're seeing gravitational waves and not something else. And it's a 2-point correlation function where we take the timing residuals from one pulsar and we correlate them against the timing residuals of another pulsar. That correlation makes one data point on this plot. So the more pulsars we have many more plots. It goes as n squared, the number of points you get on this plot. And what we should see is this very specific curve. This is due to general relativity, and it's the way that gravitational waves propagate past a source. If pulsars are really close together on the sky, they should be halfway correlated, and only halfway, because there's two things that matter. We have the pulsar and the Earth. The Earth gets jiggled in the same way towards both of them. That causes the half correlation. But every pulsar is at an independent distance, so the gravitational waves hit them at random times. That's a noise term then. So the pulsars, which is called the pulsar term, that's the scatter, this magenta scatter here. That's a noise for us, and that's why it's not 100% correlated at this side. As you spread the pulsars out on the sky, the way the gravitational waves propagate, it changes the amount of correlation you expect to see. So you should not believe anyone's detection of gravitational waves with pulsars unless they show you a significant version of this plot, because this shows that it's from gravitational waves and not something like the solar system or atomic clocks messing up or something like that. All right. So given those last few data sets, we can predict what our sensitivity is and how it's grown with time. And so this is from a really nice noise paper led by Jeff Hasboon that came out at the same time last year, showing our last three data sets, our 11-year, our 12.5-year, and our 15-year data sets, assuming all our total knowledge about what's in our pulsars and all of our noise terms, except for the gravitational waves themselves. So this is our theoretical noise curve, and what you can see is that we move down in strain sensitivity as a function of time. That's kind of that square root of n effect. We also move down much more quicker because we've added many more pulsars, and as those pulsars come into being, that lets us move much quicker in this direction. But we're also timing pulsars longer. That gets us to lower frequencies. So as time goes on, our sensitivity goes down and to the left. And you can see that the peak, or the minimum point on these curves is gone down and to the left. And the great thing about this is that our sources, back from that original black hole model, they increase in strain as you go to lower frequencies. So as we go down and to the left, we ride up that curve as well, and we get more and more sensitive to those sources with time. So we win because our sources get stronger down there as well. And sure enough, based on our 12.5-year data, we realized, we thought we were seeing noise terms in many of our pulsars, and we thought it was pretty decent evidence, even with our 12.5-year data set from three or 4 years ago, that we were seeing evidence of the background. And that shifts, if I bump back and forth, that shifts our noise, that shifts our noise curve for our 15 years, because we can't see beyond the background. But the good thing is we're trying to detect the background. So with our 15-year data set, the prediction was we should see it if it's there. And that's what we announced in June. We released, at the time, 4 papers. Actually, there was 5, but one of them hadn't been accepted yet, but now it's accepted. And since then, there's 2 other papers. They're on the special AppJ letters issue, which you can get to just by searching for NANOGrav 15-year data set. And all of them are together. And these are basically the topics, and with the rest of maybe the next 10 minutes, the final 10 minutes, I'll go through the important bits. So hopefully you saw this. This is the big result. Here's our Hellings and Downs curve. It's at a roughly 4 sigma level, depending on how you compute the statistics. So it's not at the 5 sigma level that we could say detection, but we're seeing a steep power law process. This is frequency. Here's our measurements, and you can see the dotted line is the naive prediction of what gravitational waves from supermassive black holes should look like. And it's roughly in the amplitude range where we'd expect it to be from supermassive black holes. So everything looks really good, and especially the fact that we're seeing this 3.5 to 4 sigma Hellings and Downs curve. I'm not going to go into the detail here, but we did a very sophisticated Bayesian analysis as well as frequentist analysis of our data that compares various different models. So these are our models, and we compare them with a Bayes factor. The 2 most important ones are, we knew there was red noise there. We saw that with a Bayes factor of 10 to the 12. So there's low frequency noise in our data from the pulsars. We know that. But the Bayes factor that it's caused by the Hellings and Downs curve, gravitational waves, was a couple hundred to 1. So that's where we're getting this 3.5 to 4 sigma significance. But we check for a whole ton of other stuff as well for systematics in our data. And one of the other things that makes it most convincing to me is the fact that with independent data sets from our partner pulsar timing arrays, we all see at between 2 and 3.5 to 4 sigma, we all see the same thing basically. So this is the paper that was just published a couple months ago that by the International Pulsar Timing Array, where we analyzed each of the data sets from the other teams and compared. We're all seeing a similar spectral amplitude, a similar spectral index of that power law signal. We're all seeing Hellings and Downs curves at various levels. You can see our noise curves down here at the bottom left. They're all similar-ish and are just dipping into where the background should be, and including the Chinese with the FAST telescope with only 3.5 years of data saw a tiny hint. This is their Hellings and Downs curve. It's really ugly, but there's a hint that it's real even in their data after 3.5 years using a whole bunch of pulsars. So the future is looking really, really good, I think, for this field. So what does this mean? So our Occam's razor suggests, because we know galaxies merge and galaxies have supermassive black holes, we think this is the most likely source, but is it consistent with what we know about the universe? So Luke Kelly is the head of our astrophysics working group, led a massive project using massive cosmological simulations that included galaxy mergers and a wide variety of physics that you could take in and out and tweak how that physics is done, and simulated the universe many, many times with a very clever set of techniques, and calculated what the gravitational wave background should look like based on that. And this is a complicated plot, but I just want to point out a couple things. So this is simplified into thinking that the gravitational wave background is going to look like a power law. So it's going to have an amplitude and a spectral index. The spectral index is on the x-axis. The amplitude is on the y-axis. These contours here, these guys, well, I'll use the cursor. These contours here are NANOGrav's results, our measurements. The dotted line is the prediction, assuming pure gravitational waves. Nothing else is affecting them. And you can see we're on the edge, so there's a slight bit of tension possibly there. And the simulations that only included gravitational waves are these magenta contours here. And what you can see is there's a lot of variance. So if you sample the universe, you get a noise variance in the gravitational wave background. That noise variance is completely consistent with what we see. You get even more variance on these blue curves if you add environmental effects. And by that, I mean, what if gas is helping the black holes, get closer together and is taking away some of the gravitational waves and is causing them to merge quicker? Or what if, for instance, eccentricity or triaxiality in the galactic potentials is causing the black holes to move more efficiently together? All of those environmental effects either contribute to make the black holes go together quicker, but they also potentially take away some of the gravitational wave power, because those environmental effects are what's causing, at least partially, the black holes to get together. And with those environmental effects, you can see we easily encompass the NANOGrav results. So the summary, you can see those environmental effects in this upper right here on a power law distribution. The pure gravitational waves is the purple, and if you add the environmental effects, it kind of bends over at the lowest frequencies, and that's kind of what our data seems to show right now. So the summary from our data is that basically we seem consistent with what we know about black holes in the universe, but there's a tiny bit of tension that they seem to be slightly more massive than expected, or they're merging more frequently than expected. They merge efficiently, so there's very little delay from when the galaxies merge to when the black holes merge. So they're not like being delayed by close to a Hubble time or anything like that. And there is maybe some hints that environmental effects are at play in the centers of these galaxies. So what do other people say about this in the last year? So the next slide is basically about that. So the top left is a paper that came out this year that's talking about, is there evidence in the PTA data for environmental effects or not? And in this Ellis et al. Paper, they suggest that, just like we suggested in the astrophysics paper from NANOGrav, that the data are better fit right now by saying that environmental effects are important. So in other words, black holes merge efficiently once the galaxies merge, and that efficiency, in other words, there's no last parsec problem, is caused by gas or triaxiality or something that efficiently brings those black holes close enough together, and then gravitational waves does the last little bit. So they think that the best explanation is that the environment is important. But the good thing is that we're going to learn about the centers of merged galaxies by the coming decade of PTA results. Down at the bottom left, this Sato Polito, Zaldariaga, and Elliott Hornet paper came out at the end of last year with a very interesting set of bullet points, basically. They thought that the pulsar timing array results are inconsistent with the supermassive black hole population that we know about based on local observations. They based on their assumptions, they say it cannot be explained by an increased merger rate of those black holes, and must be explained by the fact that we don't understand the black hole mass function, and especially of the most massive black holes. And they make a big assumption that the current day black hole population must be consistent with the integrated AGN luminosity over the age of the universe. So basically what we know about quasars and all of the AGN since then. And that causes them to think that there must be the black holes that are causing the, the PTA results are overmassive by about a factor of 10 from the black holes that we know about. So if they exist, they're probably invisible and we have not yet found them. So some really interesting things that they've come up with. This Leopold and Ma paper came out literally this week on the archive and kind of challenges a lot of what's there. And based on observations with the massive survey, so they're using the galaxy stellar mass function to model how big the black holes in those galaxies should be. They find no strong tension between the gravitational wave results and the local masses of black holes. And that's basically shown on that upper right plot. This plot up here shows the gravitational wave strain. Here's the levels that the PTAs think they're measuring them. And by various ways of measuring the masses of black holes, and there's, in this paper, is this magenta point here, it's completely consistent with what the PTAs are showing. And they're suggesting that the ways that black holes are being measured, that like the M sigma relation, under predicts the most massive black holes. And if you are consistent and do the best with the best data with the galaxy stellar mass function measurements, that you get results that are consistent. Their one issue is that their local supermassive black hole population seems to be bigger and more have a bigger mass density than predicted from those quasars. So that's that big assumption that they were using in that other paper down there. So that's an interesting tidbit. So, and then the other thing that I want to just bring up is that JVST, as you all know, has shown a lot of evidence for very massive black holes early on. I think the next talk in the seminar is actually exactly about that. So we think there's a lot of and more than we expected massive black holes in the early universe. They've obviously evolved over time. Are they contributing some way to the PTA background? There's been very little discussion of this yet in the literature, but I'm hoping as PTA work improves and our knowledge of the early black holes continues to improve, that we will learn more about that. But I think the interesting thing is that these measurements in the PTAs over the coming decade are going to say a lot about the black hole mass function in the universe. The other thing that's going to happen very likely within the next 5 to 10 years is that we will see individual sources, an individual supermassive black hole binary on the sky. We do not see them right now. This is based on the other paper that was led by Bensei Beche and Neil Cornish. We've done a map of sensitivity. Some of your favorite sources may be on that diagram. We've analyzed it in a whole bunch of different ways. Right now, there's no evidence for continuous waves. But one really thing that's cool and what's happened since then is there's been a bunch of really nice modeling, including by Berkeley grad student Amiko Gardner, that was just published about how very likely we're going to start seeing these sources. And even if we don't see them individually, they're going to show up as anisotropies in our gravitational wave sky maps, basically. And that will help tell us then the types of sources that we're seeing and where they're located in the universe. So this is going to be a big thing. And our biggest predictions right now, based on our current and next generation data sets, is we think there's actually a decent chance, maybe 50-50, that on our next data release, the IPTA should see our first individual supermassive black holes. Beyond black holes, though, it's possible that we're seeing new physics. And I'm not going to spend any time on this except to say there's like a 50-some page AppJ letter that we put out. If you're interested in new physics that includes inflation, scalar-induced gravitational waves, cosmic strings, all sorts of really interesting beyond standard model physics, take a look at that paper. Some of those models actually fit the data better than supermassive black holes. There's Bayes factors that are above 1 when you compare black holes versus these new physics. They're not so far, the Bayes factors aren't so significant that we believe the new physics models. But it's intriguing. And a whole bunch of papers have been published on this. This is a really cool plot. If you go to paperscape.org, you can look at all the papers that are on the archive and see how they reference each other. This dot is the NANOGrav paper here, and every white line shows the papers that have cited it since its publication, and there's many hundreds of them already. But there's papers that cover the CMB, black hole physics, inflation, extra dimensions, string phenomenology, quantum chromodynamics, gauge theory, beyond all sorts of beyond standard model stuff. It covers basically all of the archive that's referencing these NANOGrav results. So it's really interesting. The theorists are having a field day trying to explain where these gravitational waves can be coming from. One of the last things is anisotropy, which I mentioned already. This is going to be one of the key things that tells us what we're seeing. Right now, with the isotropy paper, which was led by Nihan Pol for NANOGrav, we are within 20%. We're seeing an isotropic amount of gravitational waves across the sky. But as we get better and better, more and more signal to noise, we should start seeing anisotropy come out of the data if it's due to black holes. Obviously, black holes, we're going to see the biggest and most nearby. The best estimates are we're going to see something like a 10 to the 10 solar mass binary about a gigaparsec away first. So that's going to show up as a hot spot in these maps. So we'll start seeing anisotropies. Right now, there's no evidence for it. And another recent paper that just came out, they looked at our current results and said, does it rule out black holes in any way? And it does not. Our current data are very weakly informative on anisotropies. But this is a nice paper that talks about how we're going to move forward in figuring out whether we're seeing new physics or black holes. And I should mention that most of the new physics models assume that we should see an isotropic background. My last slide is basically on the future. A lot of stuff is happening to make these measurements better. We have a new ultra-wideband receiver for the GBT, which is going to help us remove the interstellar medium effects on our data, which I haven't even talked about, but they are one of our biggest systematics. Because Arecibo collapsed, we need another big telescope. The DSA 2000 is a 2000-ish telescope that's going to be built in Nevada, highly likely within the next 3 years, an incredibly fast time scale. You should be hearing a lot more about it very soon, but that gives us an Arecibo level of collecting area on a much bigger chunk of the sky, and NANOGrav is going to get 25% of the time on that. So it'll really help our massive loss of Arecibo. Within the next 1 year, you'll see our third data release from the IPTA, which is when we're jointly analyzing all of the data sets that came out last year in a combined effort. We should see that should give us about a factor of 2 more sensitivity in gravitational waves, and it will hopefully push us over that 5 sigma detection level threshold. And then the last 2 things to mention is that the PTA results from last year really show that LISA is going to see 10 to the 6, 10 to the 7 solar mass black holes. It's kind of bumped up the minimum number that LISA should see into likely dozens of sources over its mission of the massive black hole binaries. We already know LISA is going to see a zillion white dwarfs and stellar mass black holes and stuff like that, but it's going to see dozens likely at a minimum, and potentially up to tens of thousands of 10 to the 5, 10 to the 6, 10 to the 7 solar mass black holes. And then finally, FAST and MeerKAT. When these new telescopes, which are very sensitive, and from day one, they started with 60 or 70 pulsars, timing them with modern, perfect digital instrumentation, that's the way to do this experiment. And these 2 telescopes, their sensitivity is launching compared to our current facilities. So the next decade or decade and a half in this field should be really exciting. And I will end right there. Thanks.
Great. Thank you very much, Scott. Great. Well, we have some time for questions and discussion. So if there are particular questions, I guess raise your hand in the Zoom or in the rooms, and maybe Devesh or Martian can help me in Virginia. We have Gina here at Chalmers with a question. So go ahead, Gina.
Yeah, so I was curious, is there like a horizon or a volume within which the binaries are dominating the gravitational wave background?
Yeah, so that's a good question, and there's many papers that have looked into this, and it's a real complicated weighting of distance, because distance obviously affects gravitational waves, just like it affects light, not exactly, but in a similar way. Further things are fainter. Masses, we really need the most massive binaries. Those are the two most important things, but also the merger rates. Since the mergers of galaxies have changed, that rates have changed over time. It's this integral weighting of all of those different things. And when you use cosmological simulations and stuff to figure out where we're most sensitive, like I said, we're likely to see the first individual sources, which are likely the sources that are dominating the current background. They're probably at a gigaparsec or two, and they're probably 10 to the 9 to 10 to the 10 solar mass black holes, because when you weight all those things together, that's what dominates. However, for the true horizon type question, if 10 to the 10 solar mass black holes existed at z of 20, which they likely don't, but if they did exist at z of 20, we could see them. If there was a 10 to the 10 solar mass black hole that was in our frequency band, we have the sensitivity over the next decade to see them no matter where they are in the universe. They just probably don't exist there at that time. But that's one of the things that the PTA data is going to show us, is likely where are they located, especially if we can combine our detection in this part of the sky with an electromagnetic detection, via some other method.
Great. Is there a question in Virginia, please?
We have a question in the room, yes.
Great, Scott, that's amazing. Could you go to one of the slides you show the Helix and down curve from the Chinese team? Because that's the only plot I see, like individual pairs of pulsars.
Yeah.
I know it's not from your team, but I see a lot of like correlation of 1 or -1 on this plot. Should I be suspicious of them?
You should definitely be suspicious. So this is they're heavily averaging things here, so that they say when you average all these red points, and once again I'll use the pointer, when you average all of these red dots, that you get this blue curve with these error bars. But as you mentioned, there's a lot of things that are up near 1. When you have pulsars that are correlated near 1, it's likely that there's something going on with, you're not removing the interstellar medium in a certain direction. You have an issue with the clock, for instance. Like if their observatory clock is jiggling in one way, it's going to jiggle that way for all the pulsars. That will cause more correlations. It's likely that there's some systematic that's not being 100% fully accounted for that's causing those high correlations. That doesn't mean they can't measure the Hellings and Downs curve, but it means that there's going to be more noise and their significance will be less. The other thing to really stress here is that they've taken one frequency bin, which is their longest time span, in order to make this one calculation. And so there's a lot of unknowns on how the data were taken, how they were analyzed, all on one particular time bin, or frequency bin, to make this measurement. So I think it's interesting that there's hints, but I think very few people in the PTA community right now believe their statistics 100%. And the other thing I find problematic is that all the other PTAs have shared their data. You can download all of our data. You can do the analysis yourself. You can't not do that with their data. They have not released it.
So is this like high correlation and anti-correlation value? Is that specific to this team, or is it's the same for the other team?
It's tricky because they don't show their error bars either. And by the way, for every individual pair, like if you look at NANOGrav, if you look at because all of ours are heavily averaged as well. Like if I go back to, here we go. Like this particular plot here, notice that these are binned in even bins. We don't have even sampling. We've arranged these locations, these bins. Notice they're further spread out. Oh my God, I use this again. They're further spread out on this side than they are on this side. That's just because of the locations of the pulsars in the northern hemisphere that we're mostly timing. But we've changed them. We've changed the locations of those bins to try to give equal-sized error bars. But there we have 60-some pulsars that went into this analysis. A correlation plot like this goes as n squared. So there's 3,600 measurements, roughly, that were averaged together to make those 15 or whatever it is error bars. So the individual measurements have massive error bars. So they're bigger than the size of the screen, except for a handful of very, very specific pulsars that are, more heavily weighted because they're the best pulsars. So it's very hard to know exactly what's going on. And your eye, by definition, this is a hugely integrated and averaged measurement. So yeah, that's why be a little bit skeptical, but this is also one of the reasons why we're releasing our data so that other people can do these analyses and convince themselves. And by the way, we made all the tools, the software, everything is available to do these analyses.
I have a question, Scott, if I may, can I jump in? You mentioned the results seem to imply implications for LISA, that with LISA we should see lots of relatively low mass supermassive black holes. Can you elaborate a little bit more on that, like how you can draw that to conclusion?
Yeah, so there's two. This is something I just added to the talk literally last night based on recommendations from our Astro group, because it's a relatively new papers that have come out. These two, at the end of 2023, these two papers came out based on the PTA results. So this, and what they've done, so I think there's only these two papers that are talking about the PTA implications for LISA. But they're basically saying, if they take our astrophysics paper that like NANOGrav and the other PTAs have looked at, we can predict what the mass function of the supermassive black holes are that would produce the gravitational waves that we see. That tells you something about the overall mass function, including its slope and its amplitude. And if you extrapolate that slope and amplitude down to 10 to the 6, 10 to the 5, or not even that much of an extrapolation down to 10 to the 7 solar mass black holes, you can then predict, because those are the ones that are gonna merge with the frequencies that are in the millihertz to 10 to the minus 4 hertz that LISA is going to see. That gives you the predictions for the LISA band. And there were already those predictions in the past, but we didn't know this. The way to think about it is that the uncertainty on the supermassive black hole mass function were bigger until you added this low frequency or high mass data point from the PTAs. So the high mass, the PTAs kind of give you an anchor at the highest masses, and you still have uncertainties on what the overall slope is, but it tightens the prediction for LISA. And the biggest implication from these two papers was that it raises the lower limit, because they had a lower limit of predicting 0 black holes that would be detected in the 10 to the 6 to 10 to the 7 solar mass range. But if we're right about these black holes merging efficiently and there being lots of them and mergers going quickly, then that raises the lower limit of what LISA should see to dozens of those systems. That's basically the argument, and those papers lay that out.
Great, yeah. I hope Jasbir is listening, because we have at least the numbers he's told me are a bit lower, but we'll have to see from our model. Great. Any other questions online? Please raise your hand, or here in the room.
Maybe I can annoy you, please. So about this fast merger of these black holes, you said there are environmental effects that can make this happen. What are these effects? Is dark matter also one of them that leads to a?
Yeah, could be. Absolutely. So right now we have no idea what causes the last parsec problem to be solved. But if these results are correct, and there's a bunch of ifs coming in this sentence, right? If the PTA results are correct, and if they are due to supermassive black holes, then the amplitude and spectral index that we're seeing means that they merge efficiently. And there's very little waiting time between galaxy mergers to the black hole mergers. So that means that one of the things that people have thrown out, or more than one of the things that people have thrown out to solve the last parsec problem, and triaxiality of galaxies is a big one when you actually model the orbits with proper, not assuming cylindrical symmetry and stuff like that, but add triaxiality. Gas dynamics and gas infall clear into the centers can dramatically change what's going on towards the end as well. Dark matter, the exact shape of the dark matter potentials can affect it as well. So there's a lot of different things. We don't know yet what the number 1 or number 2 things are that solves the last parsec problem. But I think the thing that people are interested in is that if the PTA results are right, the last parsec problem is solved somehow. I think that's the main thing.
And just following up on that, you measure an index of this power law that's somewhat shallow, is that right? Or
Absolutely. But
and that's in the right direction that you'd expect then from gas taking away.
Yeah, from environmental effects, yes, exactly. And you can best see that here. This is the upper right hand. Here we go. Yeah, so these violin plots right here. This is the NANOGrav data. This is our best measurement at the lowest frequency bin. And what you can see is when you have the best fit power law to this, it wants to go to the top of that violin plot if we're dominated purely by gravitational waves. If this is really on the low side, you need something that breaks this power law and softens it, makes it shallower. And that's what almost all of these environmental effects, when you include these in the simulations, they almost all cause a shallowing of that power law or a break in that power law index. But right now you can see we are not at a huge amount of tension here. There's a slight indication that environmental effects might be needed. So that's where we are right now. But all of those violin measurements this year, when we include the IPTA data together, are going to shrink quite a bit. We already have, I didn't even mention this, that NANOGrav already has an additional 5 years of data in the can because it's taken us so long to process the next one. We're already working on our 20-year data set, and each of the other PTAs are working on as well. The next decade is going to be really exciting for this field. Everything I talked about, the error bars are going to shrink, every single thing. So we're going to make really good measurements and inferences about these sources in the next 5 to 10 years.
So if it is due to gas, then that would have, I'm trying to think, it would sort of tell you how much gas you need in the vicinity of the black holes, and maybe even these cosmological simulations with galaxies would, not sure if they're accurate enough to predict how much gas is really around, but maybe that's another thing that they could be trying to predict.
Yep.
So.
And I should mention all these simulations that were in this paper that led to these blue error regions here. You can see that simulated, it says phenom. They're phenomenological models that basically try to affect how quickly the black holes are going to go once the galaxies merge into the gravitational wave dominated regime. And so they're kind of trying to be semi-agnostic on the exact physics that's causing it, but they're looking at, do we really need that? And once again, the evidence says that, hey, it does seem to fit the data better. And it indicates that we do need some help potentially getting these things in, but exactly whether it's gas or dark matter or triaxiality or whatever, we don't know that. We do not know that yet. But I think this should inform the simulations and the simulators to do better on their simulations.
Great. Are there any other questions? Jasvier, please.
Yeah, I have one question. So regarding the new JWST results, which points that there might be a higher fraction of dual AGNs at especially higher redshift, can we have some constraints from these PTA results at those high redshift, or like are they compatible with each other?
Yeah, I think that's the reason why I was encouraged to put that on the slide, is that if there's more dual and triple AGNs at the really high redshift, more than has been predicted by the simulations in the past, that implies potentially that as the evolution of the universe continues, that we could potentially expect to see more mergers throughout the history, and going to Z's of 1, 2, 3, and 4, which is probably where most of our sources are going to be. So I think it's kind of an indication that, hey, we really don't understand what's going on with early massive galaxies. And certainly we don't understand exactly how these massive black holes are evolving over time. So that hopefully this PTA work will feed into that and inform us better.
But what is that evidence for these, even the triple I've not heard about?
Yeah, so there was one, so this Perna et al. Paper, which I was surprised, it's been out on the archive for about a year and it has not been published yet. And it was in like a Nature format. So I'm sure they're arguing with like 2 or 3 referees over the last months. But you can look up that archive paper. There wasn't anything good for me to show. There was a few images, but basically they looked at something like 17 AGN with JWST, with near spec, And they found that with the resolution and with the spectroscopy, sources that they thought were likely very luminous individual AGN, 30-some% of them actually had 2 cores, so they were dual AGN, and one of the 17 was a triple system, which surprised them. But apparently, this is, like I said, controversial because it did not sail through rubbering. It is still not published yet, but go ahead and take a look.
Great. Yeah, we'll definitely look at that. Very good. Any last questions for Scott? Great. If not, let's thank Scott again for a great talk.
Thanks.